continuous load is the deciding factor when determining whether to use 600 kcmil instead of 500 kcmil wire sizes. The continuous load represents the highest electrical current a wire can safely carry indefinitely, preventing it overheating and insulation damage. This is typically determined by the wire size and the ambient temperature. A 600 kcmil wire possesses a larger cross-sectional area compared to a 500 kcmil wire, enabling it to handle a greater current. When the continuous load surpasses the rated capacity of the 500 kcmil wire, upgrading to a 600 kcmil wire becomes essential for ensuring safe and reliable operation. Several factors influence the selection of the appropriate wire size. Firstly, ampacity, which is the current carrying capacity of the wire under specific conditions. Secondly, ambient temperature, or the temperature of the surrounding environment where the wire is installed. Thirdly, the type of insulation, referring to the material and thickness of the insulation around the wire. And fourthly, local building codes may specify minimum wire sizes for different applications. Let's consider an example to illustrate this concept. Imagine an electrical circuit with a continuous load of 350 amps and an ambient temperature of 75 degrees Fahrenheit. According to the National Electrical Code, the ampacity of 500 kcmil THWN copper wire at 75 degrees Fahrenheit is 335 amps. Given that the continuous load of 350 amps exceeds the ampacity of the 500 kcmil wire, opting for 600 kcmil wire size is necessary to guarantee the circuit operates safely and efficiently. Ampacity is the maximum amount of electrical current a conductor can carry before sustaining immediate or progressive deterioration. Several factors influence a conductor's ampacity. Firstly, the conductor material. Secondly, the cross-sectional area. Thirdly, the insulation rating. Fourthly, the installation method. And fifthly, the ambient temperature. Different conductor materials possess varying conductivity levels. For a given size, copper generally has a higher ampacity than aluminum due to its superior conductivity. A larger cross-sectional area allows a conductor to dissipate heat more effectively, thereby increasing its ampacity. Insulation materials are rated for specific maximum operating temperatures. A conductor's ampacity is derated if the operating temperature exceeds the insulation's rating. How a conductor is installed affects its ability to dissipate heat. Conductors installed in free air typically have a higher ampacity than those installed in conduits or cable trays. Higher ambient temperatures reduce a conductor's ability to dissipate heat, leading to lower ampacity. The National Electrical Code provides tables and guidelines for determining conductor ampacity based on these factors. These tables take into account the conductor material, insulation type, installation method, and ambient temperature. Adjustment factors are used to correct the ampacity for conditions that differ from those specified in the tables. For instance, if a conductor is installed in an area with a higher ambient temperature than specified in the table, the ampacity must be derated. Similarly, if multiple conductors are bundled together, their ampacity must be derated to account for the increased heat generated. Ambient temperature is the temperature of the air or other medium surrounding an electrical conductor or device. It plays a crucial role in determining the safe operating temperature and current carrying capacity or ampacity of electrical components. Excessive heat can damage insulation, reduce the lifespan of equipment, and even pose a fire hazard. Firstly, ambient temperature affects conductor ampacity. The higher the ambient temperature, the lower the ampacity of a conductor. This is because the conductor's ability to dissipate heat is reduced at higher temperatures. The National Electrical Code provides ampacity correction factors for different ambient temperatures. Secondly, ambient temperature influences equipment ratings. Electrical equipment such as transformers, circuit breakers, and motors are designed to operate within a specific temperature range. Exceeding this temperature range can damage the equipment and reduce its lifespan. Equipment manufacturers typically provide temperature derating information for operating in high ambient temperatures. Thirdly, ambient temperature impacts insulation life. High temperatures accelerate the degradation of insulation materials. This can lead to insulation failure, short circuits, and electrical hazards. The service life of insulation is typically halved for every 10 degrees Celsius increase in temperature above its rated temperature. Fourthly, ambient temperature is a factor in enclosure design. Enclosures for electrical equipment must be designed to dissipate heat effectively. This is particularly important in high ambient temperature environments. Enclosures may be ventilated, air-conditioned, or liquid-cooled to maintain a safe operating temperature. Fifthly, ambient temperature affects voltage drop. The resistance of a conductor increases with temperature. This can lead to increased voltage drop in lawn conductors, especially at high ambient temperatures. Voltage drop can cause equipment to malfunction or operate inefficiently. There are several ways to mitigate the effects of high ambient temperatures in electrical systems. Firstly, select conductors with higher temperature ratings. Secondly, direct conductor ampacity according to the National Electrical Code tables. Thirdly, provide adequate ventilation for electrical equipment. Fourthly, use enclosures designed for high ambient temperatures. Fifthly, minimize conductor length to reduce voltage drop. And sixthly, implement a regular maintenance program to inspect and test electrical equipment. Insulation type refers to the material used to cover electrical conductors. It serves to prevent electrical current from unintentionally flowing outside the conductor. The selection of insulation type depends on factors such as voltage rating, temperature rating, environmental conditions, and application. Common types of insulation used in electrical wiring include firstly, thermoplastic high heat resistant nylon coated THHN insulation, which is a popular type of insulation for general purpose wiring. It has a high heat resistance rating of 90 degrees Celsius in dry locations and is also resistant to moisture and oil. THHN is commonly used in conduit and cable trays. Secondly, thermoplastic heat-resistant, water-resistant THWN insulation, which is similar to THHN but is also water-resistant. It is suitable for use in wet locations, such as bathrooms and kitchens. Thirdly, cross-linked polyethylene XLP or XLP insulation, which is a thermosetting insulation that offers excellent electrical properties, heat resistance, and chemical resistance. XLPE is commonly used in high-voltage cables and underground wiring. Fourthly, rubber insulation such as ethylene propylene rubber EPR insulation, which is a flexible insulation that offers good electrical properties and resistance to moisture and chemicals. EPR is commonly used in medium-voltage cables and motor leads. Fifthly, mineral insulation such as magnesium oxide MiO insulation, which is a highly heat-resistant insulation that is suitable for use in high-temperature applications. Mineral insulation is commonly used in heating elements and thermocouples. The National Electrical Code specifies the allowable uses and restrictions for different types of insulation. It also provides guidelines for selecting the appropriate insulation type for different applications. Some key considerations when selecting insulation type include firstly, voltage rating, which is the maximum voltage that the insulation can withstand without breaking down. Secondly, temperature rating, which is the maximum temperature that the insulation can withstand without degrading. Thirdly, environmental conditions such as exposure to moisture, chemicals, and sunlight. Fourthly, application such as general purpose wiring, high voltage cables, or underground wiring. Selecting the appropriate insulation type is crucial for ensuring the safety and reliability of electrical systems. Using the wrong type of insulation can lead to electrical hazards, equipment damage, and system failure. The National Electrical Code is a set of standards and guidelines for the safe installation of electrical wiring and equipment. It is developed and maintained by the National Fire Protection Association. The NEC is updated every 3 years to reflect changes in technology and best practices. The purpose of the NEC is to protect people and property from electrical hazards. It covers a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. Compliance with the NEC is typically required by law. Local building codes often incorporate the NEC by reference, making it a legal requirement to follow its provisions. Failure to comply with the NEC can result in fines, penalties, and even criminal charges. The NEC is organized into chapters, articles, and sections. Chapter 1 covers general requirements such as definitions and scope. Chapters 2 through 7 cover specific wiring methods and equipment installations. Chapter 8 covers communications systems such as telephone and data wiring. Chapter 9 contains tables and examples to aid in the application of the code. The NEC contains many tables that provide information on conductor ampacity, conduit fill, and other important parameters. These tables are essential for designing and installing electrical systems that comply with the code. The NEC also contains many examples that illustrate how to apply the code in specific situations. These examples can be helpful for understanding the intent of the code and for ensuring that installations are compliant. It is important to consult the latest edition of the NEC when designing and installing electrical systems. The code is constantly evolving to reflect changes in technology and best practices. Staying up to date on the latest requirements is essential for ensuring the safety and reliability of electrical installations. Several resources are available to help with understanding and applying the NEC. These include training courses, online forums, and publications from the National Fire Protection Association. Investing in education and training is essential for anyone who works with electrical systems. The National Electrical Code is a comprehensive set of standards and guidelines for the safe installation of electrical wiring and equipment. Compliance with the NEC is essential for protecting people and property from electrical hazards.